Good morning, algebra classes. It's your first actual lesson from me virtually. So basically, I'm going to go through the lesson as I normally would in class. And I'm going to tell you to pause at brief points during the video so you can work out stuff on your own. And then after that, I'll obviously just show you how to do it. So please make sure you're actually pausing the video when it's like time for you to do your own stuff. But everything will have answers provided. So don't worry too much about getting stuck on classwork. And as always, feel free to email either me or comment on the post in Classroom. As long as your comments are appropriate for everyone to read, I'll answer it there. Or if it's a really good question, email it to me. I'll just post the answer in Classroom. So let's get started. Last unit in functions, we talked about rates of change for linear functions or just for any function in general. And we're going to talk about what a rate of change would tell us about an exponential function. So let's look at following prices. Let P be the function that gives the cost P of T in dollars of producing 1 watt of hydroelectric energy T years after 1977. So here's a table of values showing the values of P from 1977 to 1987. So sorry to be dealing with ancient history here, but hydroelectric energy, like dams and rivers and stuff, like the turbines and over waterfalls, that's hydroelectric energy that we get from water generating electricity. So, is the change in hydroelectric energy linear or exponential? So at this point, I'd say pause the video for a minute and see if you can figure out, is the change in energy linear or exponential? All right, so once you've done that, let's think about these words, linear and exponential. So linear would be like a straight line. Which would basically mean that I have a constant slope somewhere. So my rate of change on the whole line should be the same, going up by like $3 per year or down by like $5.50 per year. So we want to see if that's true from our graph. And if it's exponential, we want to see the same fraction remaining. Sorry, the shadow's really in the way. The same fraction remaining or increase by the same fraction each year. So like getting 10% larger or doubling or tripling or getting 50% larger, stuff like that. So let's see. From year 0 to year 1, we went from 80 to 60. And 60 minus 80 gives us negative 20. So meaning we lost 20, or it went down $20 in that first year. And the second year, we went from 60 to 45. So we got 45 minus 60, minus that previous amount. And that would give us negative 15. So I have different slopes or different rates. So it is not linear. So to figure out if it's exponential, I could instead divide and figure out what fraction of the original cost remained. So let's see, from 0 year to 1 year, out from 80 to 60. So let's see what fraction remains. And let me get my black pen so it looks different. So let's try from 80 to 60. So I have 60 divided by 80, which gets me 0.75. And by the way, if you want to use your phone calculators, if you're allowed to at home, that's fine. Go ahead and do that. Otherwise, I will post a link to the Desmos calculator that arguably is better. And I can sort of show you the math on that later to show you why I think it's a good calculator to use. Regardless, you don't need a special calculator for this. 60 over 80 is 0.75. And let's see, 45 divided by 60 Some of you mental mathematicians might see that this simplifies to 3 over 4 and also reduces to 0.75. And just for kicks, we could even try a lower down one on our list, or like a larger rate or larger area to see if we still have the same change. So if I were to figure out like down here, I could do like 8.01 over 10.68. And if I divide 8.01 by 10.68, I will get exactly 0.75 on my calculator. All right, so that sort of proves to us that the whole time this function remains changing at an exponential rate. So the change in hydroelectric energy is exponential with a growth factor of, remember the factor is whatever remains, so it's 0.75 because 75% or 3/4 remains every time. All right. So feel free to pause and rewatching that if you need to. We'll move on to the bottom section of our page. Which expression best represents the average rate of change in hydroelectric cost between 1977 and 1987? So before you do this, make sure you understand what each of these expressions is telling you. Like, what is P of 10 minus P of 0? Like, what is the purpose of that? What is that telling you about hydroelectric energy? So pause the video and see if you could figure out like which one of these would actually give us a rate of change. And just one more hint is that rate of change should be pretty synonymous or interchangeable in your head with slope. All right, so which one of those gives us slope? All right, so you've had time to pause and look over it. So let's see, P of 10 minus P of 0. And P of 10 is basically going to tell us when T is 10, so 10 years later, what's the price? And then P of 0 is the price at the beginning. So in 1977 to 1977, that's the difference in price. So that's just the difference, but that is not rate of change. Difference in price from year 0. Don't worry, there'll be a place for you to comment on my wonderful handwriting or if I need to really improve it or not. From year 0 to year 10. That's not quite rate of change though. P of 10 is just the price in year 10. Definitely not a rate of change. This third one, P of 10 minus P of 0 over 10 minus 0. So that numerator, that's the difference from part A. That's the difference in price. Difference in price. And this, 10 minus 0, is the number of years that have gone by. So that one is, in fact, our correct answer, because slope is really the change in the y, which is our price. So 80 minus 4.51 minus, or over, over the number of years that have gone by. So I'm sorry, it'd be 4.51 minus 80 over 10 minus 0. So let's see, it'd be 4.51 minus 80. And order does matter here because, as we know, this should be a negative rate of change because as time goes by, our price is going down. So the order does matter because if I don't do it in the right order, I'm not going to get a negative answer. So 4.51 minus 80 over 10. Let's see. I'm just using my calculator real quick. Over 10. Oh, I should have done that in my head. All right, so my answer is going to be negative 7.549. And let's see, that represents the change in energy cost per year. So the price, P of T, is going to decrease by $7.54 per year on average. So you think, is that reasonable? Does the price actually go down by about $7.55 a year? Well, here it goes down by 20, 15, like 12-ish, like 8-ish, about 7-ish. So we're kind of close right here, about 8-ish, about 7-ish, about 4.5, about 3.5, 2.5. So we'll see that the rate of change is going down, but it only really matches what's going on in these couple of years right here. So we notice that our average rate of change is not actually a perfect indicator of what's going on, but we're still going to practice the skill because there are some times when it is useful. All right, so there's your task statement number 1. And let's flip to task statement number 2. Coffee shops. So here's a table and a graph that show the number of coffee shops worldwide that a company had in its first 10 years between 1987 and 1997. Again, dealing with this old-timey stuff. At least I was alive for this problem. The growth in the number of stores was roughly exponential. So like it might not be precisely like doubling every year or something, but we want to, and I don't know if that necessarily matters for this problem, but because we're going to be practicing average rate of change. So find the average rate of change for each time period to show your reasoning. So I just want you to remember the format from the last problem, and it was the change in y up top and the change of x down bottom. So we'll sort of get the first one set up for you, then I'll give it a pause, and we will, you can give it a pause, you can give it a try, and then we'll just go through the right way to do it. So for the first one, we went from, let's see, I'll just do number after a given number of years. So I'll just do n of, let's see, and I'll keep my order the same. I'll just do bigger to smaller year because that makes sense to me. 1990 minus n of 1987, and divide that by the difference in years, 1990 minus 1987. So that should be your setup for all three of them, just noting the different years. All right, so let's give it a try. I'll do the first one just with you, and then I'll just post the answer to the next two because they're all the same process. So 1990, there were 84 stores. 1987, there were 17. And then that difference of years is 3. So 84 minus 17, let's see, minus 10 is 74, minus 7 is 67, over 3. And that'll get us 22 1/3. So that one's 22.3, approximately 22.3 stores per year. So here are your calculations for the rest of them. From 1987 to 1993, you should have had 42.5 stores per year. And 1987 to 1997, 139.5 stores per year. So basically, you might use these calculations if you're in the business world and you're describing your company's growth over time and you don't want to describe it exponentially, you want to say, like, on average, what have we been doing? On average, it's like about 22 stores per year, about 42 stores per year for those 6 years, and about 139.5 stores per year for those 10 years. And we're going to evaluate these claims down below. So make observations about the rate of change you calculated. What do these average rates tell you about how the company was growing? We already kind of talked about that. It's the approximate number of stores added each year. So let's just evaluate them now below in number 3 and say, how accurate did the average rate of change describe the growth of the company in the first 3 years? So we're just going to compare my rate of change to the numbers I see in my table. So in my first 3 years, I went up, according to my calculation, 22.3 stores per year. So the first 3 years, once again, is 22.3, close to these numbers. So from 17 to 33, it went up by like 16. So it's like, it's off, but whatever. From 1988 to 1989, it went up 22 stores. So that's pretty dead on. And from here to here, it went up by 29 stores. So it's not bad. It's okay. It's fairly close. So it's fairly close to the actual changes of 16, 22, and 29. Let's look at the 42.5 for the first 6 years. Now we know that for the first 3 years it went up by much smaller amounts, because the first 3 years it went up by, let's see, 16, 22, and 29. And then, so that's how many stores per year. So that's the 42 overestimated that. And then from 84 to 116, let's see, 16 to 100 and 16 more gets 32. We're still underestimating. From 116 to 165, that goes up by, let's see, 9 gets you to 125, so 49. Because now we're underestimating, 49, and then almost 100. So again, it really looks like this one really did not seem like a very good estimate at all, because this went up by like 87? No, I'm sorry, 107. I can do math, 107. So 42.5 is fairly inaccurate. It's fairly inaccurate because in no year did they add 42. No years added 42. Only, oops, I spelled only wrong. Only 1 year was even close. So you might be ahead of me here and thinking the last one is going to be nowhere near. And we had 139.5 stores any years? Well, let's just look. Here we added 107, not 87. Here we added 153. That's close. And then after here we see we're adding well over 200 stores, well over 300, and almost 400 stores. So this one is extremely inaccurate. So rates of change are really not so great at calculating long periods of time. The short periods of time were okay. But the longer periods of time, this is very, very inaccurate. And if I were to look at my graph and draw a straight line in my first 3 years, like a slope, constant rate of change is a slope, a straight line. The first 3 years, I could draw a pretty good straight line. Like if I was to do a linear model, line of fit, back to our unit 3 or whatever it was, that straight line's pretty good. But from 0 to 4, 5, 6, that straight line is a fairly bad predictor. And from 0 to 10, just forget about it. That prediction line is completely terrible for predicting how many stores were added each year. If you were to draw that fit line, you better say that is an awful fit line. All right, so there's that. This page of it, at least, I would say in class, we would have pretty much independent time to work on this on your own, because this is something that you could easily do independently or with the help of a table. So I want you to try this page on your own, and even if you just have the online page, if you haven't printed it out, just like try to jot things down on line paper if you have it, or even just a doc to go along with it. Feel free to input suggestions you have for making this easier for you. But basically, you should be able to figure out average rate of change for those years, see if she's right, for those years, and see if she's right. And then number 3, sort of flashback, creating an exponential function. And just a reminder, because I am getting some questions about just exponential functions in general. Exponential functions should look like, let's see, it's p is your y variable on my graph. I got p equals, and it should have that initial amount times whatever your growth factor is, or your amount that remains, raised to the t power. All right, so give that a try, and I will just post the answers when I have it ready. So here's our solutions we got. So for number 1, we just set up more of those rates of change, or more slopes. So p of 5 minus p of 0. According to my graph, p of 5 is about 19, p of 0 was 80, So subtract 19 minus 80 and 5 minus 0. Negative 61 over 5 gets me negative 12.2, which is pretty dang close to falling $12 per year. So that's right. And the second 5 years, from 1983 to 1988, be mindful that's actually 83 is the 6th year and 88 is the 11th year. So P of 11 minus P of 6 should get me 4, approximately 4. If you said like a different number, like 3.5 or 3 or something, like that's pretty close. Don't say 5. It's not 5, obviously. It's a little bit below 5. And then minus 14.5 over 5. And again, if you didn't get 14.5 for 6, like it's pretty dang close to 15. You probably could have gotten this thing 15, but it is a little bit below 15. Or even 14, you could have said that, or 13, whatever. Whichever one you said, you would have gotten something pretty close to negative 2, so about $2 per year. If the trend continues the next 5 years, would that be more or less than $2 per year? And so our rate of change went from down 12 per year to down 2 per year, so you can assume it's definitely going to be less. The average rate of change is decreasing over time because this graph is getting flatter and flatter. It's going down less and less. They can only make this energy that much cheaper. And then for my rate of change, I know my graph starts at 80. And from year 0 to year 1, it went to 60. So 60 is what fraction of 80? 60 divided by 80 gets me 0.75. So that's my growth factor. And if I wanted to check that for the next 2 years, from 45 to 60, 45 remained out of that 60, which again, 45 out of 60 is 0.75. That's where my growth factor comes from. That's what I want to say is that's the end of the lesson, really. I'll post a couple more things. The other thing that's going to be posted along with this is the lesson summary, which will go through some of the finer points of the lesson, have similar problems. So if you're stuck, try to read through this. And hopefully that will make things clearer to you. I'm not going to read through it with you now because you can just read it on your own if you need it. The other things I'm going to post are practice problems and the exit slip for today. And I will post answers to the exit slip at the start of your next lesson. So once this one's done, you can see how you should have done it. So you won't see that today, but you'll see it next time. And I'll post practice problems and I'll post the answers. I probably won't post a video. I'll just post the answer key to the practice problems. Feel free to comment with questions on that. Definitely don't be spending more than 70 minutes on class every day. I know we get 70 minutes in class, but spend an appropriate amount of time. Ask me questions. I'm here to answer them. So hopefully it made sense.